Hey everybody, this video is about the replication crisis. This is a term maybe you've heard before. It's a term people sometimes dispute, but the question is, what is it? What are they talking about? And then what are we doing about it as a scientific community? How are we responding to this? So cast your mind back to 2011. This is the year of Occupy Wall Street, of the Arab Spring, a lot of social upheaval going on. It's also the year that this paper was published. This is in the Journal of Personality and Social Psychology, a flagship journal for those subdisciplines within the field of psychology. And the basic argument of the paper is that people have precognitive abilities. People can feel or perceive the future before it happens. In fact, it reports 9 experiments with over 1,000 participants that finds that there is a small but statistically significant difference between what people are able to do and what you would expect by chance. So here's the basic design of some of these studies. Participants are presented with a blank screen, divided into the left and right half, and they're told that an image is going to appear on one side or the other, and they have to guess which side it's going to appear on. You'd expect from random guessing that their success rate would be about 50%, and that's exactly what Daryl Bem in this paper found for certain kinds of images, sort of neutral images. But for certain especially engaging or interesting images where people might actually be interested in seeing them before they appear, the success rate was higher, about 53%. So as the abstract states, that is statistically significant. That is better than you might expect by chance. It is improbable if people are just guessing by chance. And so here it is, 9 experiments showing people have precognitive abilities. I'm told that the editorial board at JPSP was conflicted about whether to publish this paper. On the one hand, they kind of all thought it seemed a little bit crazy. It's like, this violates the laws of physics as we know them. This doesn't seem like it could possibly be real. But on the other hand, this paper meets the standard methodological and statistical sort of criteria that the journal used. So there was this dispute about, well, we can't just say no to this paper because we don't like the conclusion. So they published it. But they also published this companion article in the same issue, which argues that the results of Daryl Bem's studies were probably false positives. In fact, they argue that we should not conclude that we have precognitive abilities, but rather that there's something wrong with our standards of evidence. The standard practices we're using to decide whether or not we've identified a real effect are not working properly, and we need to change something. This pair of articles kicked off a lot of discussion about how reproducible or replicable scientific results are, and they started some large-scale efforts to try to estimate how many studies, if we were to run them again, would replicate. How many of them, if you ran that same study again, could you get the same result? Probably the most well-known of these large-scale efforts was conducted by the Open Science Collaboration and published in the journal Science in 2015. Now, what these authors did was try to take 100 studies from the published research literature in psychology and do as close as they possibly could the exact same thing that the original authors did in the original study. Then they wanted to see, do you get the same effect if you do it again? And what they found was about half the time you do, and the other half you don't. So in other words, if this is a representative sample of studies, then you should think for any given study, any result you find in a published paper, there's probably about a 50-50 chance that it's real. That's kind of shocking. Now, in economics, people have tried to do something similar. Much smaller sample of studies, only 18 in this case, but it was a pretty similar result. About half of them replicate, the other half don't. Now, lest you think this is a problem only for the social sciences, preclinical cancer biology appears to have a replication rate of about 11%. Things aren't always quite so dire. There are some fields that do better. For example, experimental philosophy has about a 70% replication rate. But this got people very concerned. So in 2015, 2016, Nature actually conducted a survey of scientists to see what people were thinking about what's going on here. So in this sample, they've got about 1,500 scientists across a whole bunch of different fields, and they asked them, do you think there is a reproducibility crisis? 90% of them said yes. I'm a little confused what the 38% mean when they say there's a slight crisis, but if we count them, then 90% of researchers say, yeah, there's some kind of crisis going on. Now, this might not be a fully representative sample of scientists, Because you might think people who are more concerned about these kinds of issues would be more likely to respond to this kind of survey. But it suggests that there is something really important going on. In the survey, they also asked people, have you ever failed to replicate a result? Either something you had done on a previous occasion, you're doing a kind of internal replication, or something you found in a published paper. Across a bunch of these different fields, they found it is incredibly common that people fail to replicate something. So if we are in fact experiencing a crisis, then what are the causes? Why are replication rates so low? I like to think in terms of what I call the four horsemen of the replication crisis. These are publication bias, small sample sizes, p-hacking, which I'll explain in a moment, and harking, which stands for hypothesizing after the results are known. So let's start with publication bias. Here the idea is journals generally publish only statistically significant findings. So researchers generally only submit studies with significant findings. And this means that if you were to look at the published literature, you would have a very skewed view of the total body of evidence. Suppose 10 research teams all independently think of testing the same research question. So they each run a study, testing a hypothesis. 9 out of 10 of them find no effect, but 1 does. Which study is going to get published? Well, the one, of course. So if you were to look at the literature, you'd see this one study. You'd think, well, there isn't a ton of research on this topic, but the existing evidence clearly supports this hypothesis. But you wouldn't realize that there were 9 out of 10 studies on that topic that found no effect. And if you did know that, would you think it was a real effect? Or would you think that 1 out of 10 is a false positive? Probably it's a false positive. Small sample sizes. It's well known that a small sample can increase your false negative rate, right? The less evidence you have, the harder it is to find a significant effect. But it's also the case that a small sample size can increase your false positive rate. This is because results with small samples are far more susceptible to outliers. A few unusual people in a sample of 20 can completely change the results. Just randomly, you might get a person who scores really low on the dependent variable in a control group, and a person who scores really high on the dependent variable in an experimental group, and it's going to start to look like there's some kind of effect there when really there's not. If you, on the other hand, you have a sample of 200 or 2,000, well, then outliers become far less influential. P-hacking. So since journals only or mostly publish statistically significant findings, researchers are very strongly incentivized to produce statistically significant findings, right? Publications are the coin of the realm in academia. So you really, really want to get that p-value less than 0.05. Hence, if your first analysis isn't significant, well, then you might pivot to another sort of analysis or another. You might start to get creative with the data to see what you can find, right? I think the easiest way to understand this idea is with a demonstration. For this demonstration, I am on the 538 website where they have this very cool tool that is useful for demonstrating p-hacking. Suppose we're interested in the research question of which US political party is better for the US economy. Well, if this is going to be a scientifically testable research question, then we had better specify our variables. So what I mean by a party is better for the economy is I'm going to say I think Republicans are better for the economy in that when a Republican is president, then the stock market tends to perform better. Okay, so the results for this analysis suggest that that's not true. But you know what? Wait a minute. This is oversimplifying things. We don't just care about stock prices, we also care about GDP. That didn't make a difference. But wait a minute. The president is only one member of the executive branch, and we also need to be thinking about the governors. There's so many more of them. And wow, look! Now what we found is that the Republicans have a negative effect on the economy. That's not what I was originally hypothesizing. You know what? I think maybe we're looking at the wrong outcomes here. We shouldn't be thinking about stock prices and GDP. We should be thinking about jobs, unemployment. Wow, wait a minute. And then if I include inflation, oh, wow. So look, now the Republicans are good for the economy. As you'll probably have quickly realized, depending on how you play around with these things, you can get completely different results. So this is p-hacking. It's playing around with the data, looking at different variables, adding different control variables, all this different kind of stuff to try and get yourself a p-value less than 0.05 so that you have a statistically significant publishable result. This is one of the first papers to raise awareness about this as a problem, and they really focus on the flexibility that people have in data collection and analysis and why that's a problem. The point that they make is, if there really is no effect, if the hypothesis you're testing is false, and you have flexibility in your data collection and analysis, then you can still actually have a more likely than not chance of finding a statistically significant result. So they give this nice kind of fun example. Here's a sort of fake study. It's a real study with real data, but it's used purely for demonstration. So they say, we recruited 20 participants to either listen to When I'm 64 by the Beatles or Kalimba. Then they reported their birth date, and they also reported their father's age. We controlled for father's age to account for variation in baseline age, whatever that is. And then in ANCOVA, we found the predicted effect. According to their birth dates, people were a year and a half younger after listening to When I'm 64 rather than Kalimba. P-value 0.04. Here's what they didn't tell you. We actually recruited 34 participants. Some of them were in a third condition we didn't tell you about, where they listened to Hot Potato by the Wiggles. Also, we collected data about 10 participants, then we ran our analyses, then we collected 10 more, we ran our analyses, then we collected 10 more, we ran our analyses. We didn't tell you about that. We also didn't decide in advance when we were going to stop collecting data. In addition to their birthday, we also asked people how old they felt, how much they would enjoy eating at a diner, the square root of 100, their agreement with computers or complicated machines, their father's age, their mother's age, whether they would take advantage of an early bird special, their political orientation, which of 4 Canadian quarterbacks they believed won an award, how often they refer to the past as, quote, the good old days, and their gender. They didn't tell you about those. Those could have also been covariates included in this analysis or tested for interactions with those kinds of things. All kinds of stuff that you could play around with all of those extra variables. Now, if they had reported all of this and not just the bolded stuff, would you have ever believed, regardless of what the content of the study was, what hypothesis it was testing, would you ever have believed that this was a real effect? Probably not. But if they don't tell you about any of that, then you have no way to know. You just look at the results and you say, wow, there's a real effect here. The last of our 4 horsemen is harking, hypothesizing after the results are known. So this is defined as presenting a post hoc hypothesis, that is one that's based on or informed by your results, as if it were in fact an a priori hypothesis, something you predicted before you ran the study. Right? Now, this is kind of close to something that's really not a problem, which is having an evidence-based theory, right? Like that's a good thing. That's what we should be trying for. But the problem is when you pretend like you predicted something that you didn't. Not only is that dishonest, but it's also likely to propagate flukes as validation of existing theories. Now, it's important to distinguish harking from doing exploratory research where you play with data, find something interesting, speculate about why it might be, and then run a confirmatory study. But that last step is very important, and being transparent about how it actually happened is also very important. So what do we do about this? What's the solution to these problems? Well, in the case of small sample sizes, I think the solution is pretty straightforward. We just get bigger samples. But things are a little more complicated when it comes to p-hacking and harking. The standard thing people now will recommend is pre-registration. So the idea of pre-registering a study is before you run the study, before you collect the data or analyze the data, you actually just lay out all of these decisions that you're going to have to make eventually in advance. And you put them in this time-stamped document so it's very clear to yourself in the future and to reviewers and readers what you actually planned, what you actually hypothesized, and how you plan to test the hypothesis. This is important because it's so easy to forget these things, right? Like the time between when you first plan out a study and when you actually have the data in hand tends to be rather long. So it's just incredibly easy to forget, what did we originally hypothesize? How did we plan to analyze those data? What control variables, if any, did we think we were going to include? All of these different things that you can play around with to p-hack, you genuinely can forget what you originally said. So having that pre-registration document is a really helpful tool. It's also incredibly easy to deceive yourself. If you've got this freedom and flexibility to do whatever you want with your data, it is so easy to play around with it, find something statistically significant, then look back and say, well, obviously we should have said this in the first place. This is the much more reasonable, appropriate way to analyze the data. If we had thought about it more clearly, we would have come to this conclusion in advance. Would you? Right? Like, it's just the possibility for self-deception is just so important and easy to fall into that trap. So pre-registration is there to keep the honest people honest. Publication bias? Well, if the problem is that journals basically only ever publish statistically significant results, well then isn't the solution to just publish null results? This is kind of disputed. I put that question mark there because people kind of don't know what to say about this. There's no consensus. On the one hand, it would potentially solve this problem, but on the other, it's often very unclear what to make of a null result. The evidential value is often not clear because it could mean that there is no effect. The hypothesis that you were testing is false. But it could also show that there's just something wrong with your study. Maybe you didn't have a big enough sample. Maybe you didn't have a good enough measure. Or maybe you looked at the wrong context, or who knows, right? Like, there are all kinds of things that could explain a null result, such that people often don't know what to make of them. The other problem people sometimes point out about this as a solution is that there's already an enormous amount of research being published. The volume of work is so hard to keep up with that if we then put in all of these null results too, then it's just exacerbating that existing problem. So another thing people have proposed as a solution is a registered report. This is a little bit like a pre-registration, but importantly different. It kind of inverts the typical process of publishing a paper. Typically, traditionally, you would run a study, analyze the data, write up a paper, send it to a journal, and then the journal sends it to reviewers and they try to decide whether or not they want to publish it. In a registered report, you first plan out your study, you write like the intro and the methods, and then you send that to the journal. The journal asks the reviewers to comment on the design of the study. Is this an important, interesting question to test? Is it being tested in a rigorous way? If they like it, you get an in-principle acceptance. So then you go off, you collect your data, you analyze it, you write up the results in a discussion, you add that to what you'd already included. And then if you did what you said you would, the journal has guaranteed that they will publish the result, regardless of whether or not they're statistically significant. I think that's a very cool way of doing things, and probably in many ways the future of scientific publishing. More generally, I think this is all part of this broader movement towards what we call open science. The idea here is that everything researchers do should be done in an open and publicly accessible way. The data should be public, the materials used in the study, the decisions that were made in advance and those that were made along the way, all of that should be documented and made accessible to anybody who's interested. The resulting paper maybe could be open access, or at least a preprint of it. The peer review process could be made open so people can see, what did the reviewers think of this? All of this is part of just bringing science out from behind the curtains and the closed doors to reveal what's really going on. And that might make it more trustworthy. It might make the replicability rates go up. Obviously, there's a lot for the scientific community to keep thinking about in terms of exactly what this should look like. But in my view, this is the future. I think this is where we're headed. And I think that's a good thing for science.